Okay, hello, Roger. It's my great pleasure and honor to introduce our next speaker, Sir Roger Penrose, who will be talking about why the symmetries of microtubules in a relativity theory may have unexpected implications for the timing of conscious actions. Let's give a round of applause to Sir Roger Penrose.
I hope you can hear me. Can you? Can you hear me?
Yes.
Oh, good. Can you see the screen?
We can see the slide and we can see you in the corner. So everything's perfect.
Okay. Yes. I'm afraid I don't have anything nearly as interesting as what we've just heard, but I'll just tell you a few things which I've been thinking about, not necessarily recently either. Uh, Let me move on to well, first of all, the question of symmetry. And Stuart told me that since this session has to do with symmetry and dimensionality, and I couldn't think of anything I could say which did to do with that, but he told me it was my fault that he's named this after these concepts. So I had to think hard about how symmetry could be relevant to things that I might talk about. And there is one thing in particular with regard to microtubules, which maybe has some interest. So here we have a microtubule. I should say I should apologize for the top right-hand corner because I gather, Stuart, this is an old slide and the idea that it had to do with conformations seems to be outdated now, but never mind about that. This is a picture of a microtubule, which I must have drawn a long time ago. And you can see something about the lattice structure along the microtubule. Now, I should explain first that the general idea I had about consciousness was a long, long time ago, and I was impressed by learning about Gödel's theorem and that there were things that seemed to be non-computable, that understanding, the quality of understanding seemed to be something that you couldn't define in terms of algorithms. And if that was the case, then there has to be something, since our brains are physical objects, there has to be something going on in our brains which is part of the physics, which might be outside computability. And the only thing which I could think of, which could possibly be play a role of this nature that be uncomputable, was the collapse of the wave function, because all the other features of physics seem to be something where you could put them on a computer. Of course, their current physics depends on the continuous variables, and so your calculations are always approximations. There is a possible loophole there, but I didn't think that was like to be the answer to this puzzle that I was having, to find something in physics that could be non-computable. And I thought about general relativity and electromagnetism and all these things, and it didn't seem there was much hope because you could put those on a computer. What about quantum mechanics? Well, you can put the wave function on it. I had the view that it was the collapse of the wave function which somehow had to be outside what you could compute. Now, current understanding is that it's a random process. It would have to be something a little more subtle than that if it's going to be something which is involved in consciousness. Never mind, we'll come to that question later, perhaps. But anyway, I wrote this book, The Emperor's New Mind, where I tried to express this idea that maybe the collapse of the wave function, well, in order for it to play any role, you had to have quantum systems going on in our brain, which could be sort of big enough, in a sense, that you could preserve coherence to a significant level. And I learned about the Hodgkin-Huxley nerve transmission, and I thought there wasn't a hope because the signals down neurons would disturb the ambient material in a sort of random way, and there's no way you could preserve coherence just with nerve transmission. So I sort of petered off at the end of my book without having an idea. But then Stuart read my book and told me about microtubules. And the microtubules then were the main difference between the first book here on the left and the second one, where I realized there might be something in microtubule behavior, but I didn't have much idea about it. Okay, well, let me come back to the microtubule. The only thing I wanted to say now, which I hadn't expressed before, has something to do with the structure of microtubules. And you can think of a microtubule lattice as being something like a hexagonal lattice, which has three different directions in which it repeats itself. And but then you roll it up into a cylinder. Now, if you think of it locally, then there are these three different directions. One is when it is rolled up into a cylinder, one is sort of corkscrews around one way, another one corkscrews the other way, and the other one translates along the length of the microtubule. Now, it always struck me as rather strange that the microtubules you find here have this particular symmetry which goes along the microtubule itself. And it's possible, I gather, in a dish or something, you can construct all sorts of microtubules which have different numbers of columns. You see, the microtubule has 13 of them. If you change that number to 14 or to 12, you can certainly have microtubules, but then they lose this translational symmetry. They're all twisty, one way or the other, but they're twisty symmetries. Why does the microtubule seem to have this seems purely accidental, this translational symmetry along the direction of the microtubule? And this reminded me of something I'd seen in some discussion of carbon nanotubes. And you can have them with all sorts of different symmetries. And it seemed to be the case that those which had a symmetry, translational symmetry in the direction of the tubes, they would exhibit superconductivity. And superconductivity at room temperature is something which, well, you can, maybe they can do it with these nanotubes. But I'm not sure I can even remember which this article I was looking at. Maybe somebody could find it out for me. But in the study of these carbon nanotubes, it seemed to me that when you have this linear symmetry, not just the twisty symmetries, the corkscrew symmetries, but at least one symmetry which is translational. And that this was something present in these particular carbon nanotubes, which happen to exhibit superconductivity. So it's suggested to me that there might be some kind of role which is played by microtubules. Excuse me. Where it would make use of this additional symmetry. And I can't see really much more about this because I never thought about very much more. It just seemed to me that there is something which should be explored. Maybe there is something particular about the microtubules which you find, and they have this translational symmetry, which could perhaps accompany some quantum effects which could be more global than the ones we normally find. Now, I don't want to say too much more about that because really what I want to talk about is something different. First of all, let me talk about the quantum evolution of the quantum state. Excuse me. There are two procedures. One is this Schrodinger equation. You see, people often, when they talk about quantum mechanics, they just talk about the Schrodinger equation. They sort of the collapse of the wave function or something which is sort of rather embarrassing to quantum mechanics because it's not really part of quantum mechanics to have a theory of that. It's just that when it changes the quantum amplitudes into probabilities, and how you go from one to the other is not really explained in current quantum mechanics, certainly in conventional quantum mechanics. And what just has these two procedures. the Schrodinger equation and the collapse of the wave function. Now, the Schrodinger equation is a smooth, computable, if you like, and deterministic process. It's like Newtonian mechanics in that respect, but it's just the ordinary kind of thing. You just follow the Schrodinger equation, and it gives you this smooth evolution, which is deterministic. Collapse of the wave function, as we understand it, is random. It's a completely different kind of process. And why do we go from one to the other? How do you have a theory which encompasses both of them at the same time? There's a little thing which may be a point which I thought about recently when people talk about, I think it was I'd heard about a lecture which was been given concerning free will in animals. And the question is, how could you tell whether the animals had free will or not? I mean, how do you know? And then I began thinking about what do I say about free will? I mean, is the collapse of the wave function, I know Stewart often says it gives you scope for free will, but free will, what does it really mean? And people often talk about it. Well, you can be, in fact, there were some of these Libet experiments, I believe, when people tried to be as random as they could. And the question was whether they were really being random or not. And the free will seemed to be the quality that you could be as random as you like. Now, that really can't be the answer. It seemed to me that it isn't really the answer. Because if you want to ask if something has free will, well, that means they're using their conscious experiences or conscious understanding or something to do what they want to do. Now, doing what they want to do depends upon probably some kind of process which they go through, which tells them that this is the right thing to do. Now, I'm trying to say that conscious activity is something which goes beyond computability. Now, you see, the freedom that you have in consciousness, or the freedom of free will, is not the freedom to be random. That's not the point. It's the freedom to do what you think is the right thing to do. It may be the wrong thing to do, but what you think is the right thing to do. And that depends on your conscious understanding. So I'm trying to say that, again, it has to be something which is not random. It has to be something which is controlled by some kind of thing which is deeper than random. It's non-computable, some kind of process which is involved in the collapse of the wave function is the idea. Okay, well, let's move away from that. Sorry, I think I'm going the wrong way in my pictures. Just a second. Doesn't work. Okay, now quantum superposition. Let me talk about that first. You see, the quantum superposition is what these quantum processes involve lots of quantum superpositions, and they get you can have a system which involves an environment, and then the environment gets too complicated, and then you want to know what it's doing. Well, the idea is it would still, if you don't have the collapse of the wave function, it would follow the process of quantum superposition. Now, what quantum superposition is that if you have state A or a state B, both of which are allowable states, then so also is a state alpha A plus beta B. Now, alpha and beta are complex numbers, so they involve the square root of -1, and I always found this very remarkable because I learned about complex numbers when I was doing my undergraduate course, University College in London, and I didn't know anything about quantum mechanics at the time, and I thought, wouldn't it be wonderful if physics somehow used these wonderful numbers and the wonderful mathematics that they derive? And it wasn't until I learned about quantum mechanics that I realized that they actually do play this fundamental role. Now, the thing is that if you're thinking of A as being some object in one location and B as being the location in another object, then it's a bit hard to imagine how you can have a combination of alpha being in one place and beta being in the other place. I remember Dirac in his lectures, which I went to when I was a graduate student, and he tried to explain about the superposition, and he had said you have an atom in one place, or it could be in another place, and then there were various states where it can be both at once. And then he gave some explanation of why you didn't normally find big things like pieces of chalk in two places at once. And I remember being distracted by something that was going outside the window, and I never heard his explanation, which is probably a good thing, because his explanation was probably something to calm me down and not worry. But it seems that is something that I felt I needed to worry about, and I didn't hear his explanation, which was probably a good thing. Anyway, let me explain that quantum superposition is very fundamental to quantum mechanics, and it's not something which just says that if something can be over here or over there, then you have these funny looking states where it could be both places at once. It really is a central part of, well, I thought one of the things that's very nice to do is think about spin. And the spin of a spin half particle can be described as the general state of a spin half particle can be described as take some direction in space, and then it's right-handed about that direction. Now, the thing is that there are really two different states, or two different independent states of a spin half particle, and they can be spinning right-handed about the upward direction or about the downward direction. And then all these different complex combinations of the two are represented by these linear combinations, and they are with these complex numbers. And you see this relationship between these wonderful complex numbers and the structure of space. And I found this extremely striking and remarkable. And there is nothing special about up or down. All the other combinations are on equal footing with them up or down. So if you have a state like this, then you can see that there's nothing special about one or the other. All the different combinations are just as good as the individual ones. So that's a nice example showing you that. Now, much later, when I started worrying about how to bring quantum mechanics and relativity, general relativity theory together in some sort of way, I realized that you needed to have something like a collapse of the wave function. You see, there are the two basic principles. Quantum mechanics is this superposition principle, which I've just been talking about, and general relativity, it's the principle of principle of equivalence, which is saying that locally a gravitational field can be eliminated by free fall. And one can show that, that these two basic principles are essentially incompatible with each other. That if you try to have them both at once, you're led to a limit in the time scale of the superposition. So that this was what drove me to a particular lifetime for a superposition, which is given by this formula here. I learned later that 2 years earlier, Dioschi had come to the same conclusion using some different arguments. Anyway, that gave perhaps the fact that there was another way of doing it was an additional reason for perhaps taking it seriously. But the argument is that if you have a quantity called Eg, which I'm calling the well, that's the energy, if you take of a superposition, it's the gravitational self-energy of the difference between the two states. And if it's a spin half particle, then there isn't such a, the thing could go on forever because it's, there's no such energy difference here. But if you take say, piece of chalk in two places at once, then there is this energy difference. You take the energy, the self-energy. Well, it's better to explain it another way, which is at the bottom of the slide. I don't quite know why it's got slid down at the bottom. At the bottom of the slide, we have, you can describe it in another way. You could say that the two bodies, you can think of a body in a superposition of two locations. What is the EG? Well, you think of that body, two instances of that body on top of each other. Then you try to move them apart to the place where they're in superposition and ask how much energy would that cost you to move them apart when you consider only gravity. You have to ignore electric forces and nuclear forces, all these which are much, much bigger. You ignore all those other forces. You just take the gravitational force to pull them apart, and how much energy would that be? And this is this quantity Eg. So that's the quantity Eg now. Okay, well now let's try and get back to the symmetry question. You see, if you have a fundamental thing like this, which is supposed to be consistent with relativity, then it has to be consistent not just with general relativity, it has to be consistent with special relativity. So if you're considering your moving frames and things, the theory has to work with different frames. So I have here a space-time picture. I'm imagining a body right at the bottom of the picture. It's put into a superposition of two locations. As you move up the picture, they get further and further apart. At a certain point, they collapse to one. So it goes to the location Q or the location Q star. Let's say it goes to Q star. Now, I want to describe this picture in different spaces, different frames. You see, I'm using now the symmetry of special relativity. Special relativity has a symmetry, so I wanted to bring symmetry into the argument, and so that was the point I was doing this here. I was explaining the fact that you have the symmetry of special relativity is a little bit of a problem when you consider this Diochy scheme. You see, how do we suppose this? I imagine the body is at the bottom. It's superposed into two locations, and then eventually it goes to point Q star rather than Q in this case. Let's go say it goes to Q star. Now, if I describe this picture according to ordinary, let's say ordinary description, you'd think of your horizontal slices through the picture, giving you what happens. And it goes on, chugs away, and then at a particular moment, the superposition becomes Q star rather than Q, and then Q has disappeared and it becomes Q. But how you suppose we describe this picture according to some observer? Let's not hold it an observer because there's nobody really looking at it. But some frame of reference which is moving rapidly over to the left or to the right. It has to be with less than the speed of light, but let's say it's if it's moving to the left as you go up, those are the T ones where it's the other ones. These are the S ones where what is regarded as simultaneous with regard to that frame of reference. It would be that the slope up, the ones you see S0 and S1, those are two descriptions which would be regarded as simultaneous to the observer moving up to the left. And that one, you see the Q star would have become the whole state before the Q has actually disappeared. You see, there's still an amplitude for Q to be there when the whole state has become Q star. And that doesn't make any sense because that means there's still a probability that it might be Q and then it could be both places at once, and that makes nonsense. It's even worse for the other state, I suppose, because that's moving off to the right and then the slope is the other way around. These are the T's, and T0 and T's, there's no problem there. But when you get to T1, you see that one of them has already disappeared and the other one hasn't quite made it up its mind yet whether to disappear or not. And that doesn't make any sense because it might disappear still. And that doesn't make any sense. So the picture doesn't work. The picture doesn't work for the collapse of the wave function unless you go right down to the point O. That is to say, the reality of the state was all the time the left-hand one. But what do you say about the superposition? Well, to make sense of this, you really have to have two different notions of reality. And I'm calling these two notions classical reality and quantum reality. The quantum reality, it's true that there is this superposition. And this is the less robust kind of reality. And it's a little bit hard to pin it down. The classical reality is the one which goes off to the right. And that is, you have to make a distinction between the two kinds of reality in order to make sense of this idea. Now, I'm not sure I got the right, here in movie. Quantum reality. Now, quantum reality is really defined by a notion introduced by Einstein, what I'm calling Einstein's dictum. He says, if in any, well, my eyesight is too bad to read it, perhaps you can read it. The concept is that if you can perform an experiment on a system, and that system is not changed by the experiment, so it leaves it alone, and it gives you an answer with certainty, then that gives you a reality to that state. So this kind of reality is what I'm calling quantum reality. Einstein didn't distinguish it from any other kind of reality, I think, but it is what I mean by quantum reality. And that's, I got 1935, I think, is when the statement came from him. This is a quote from Einstein. So quantum reality is defined by the Einstein criterion. And this is the kind of reality you have here. So if you imagine a state of spin, which might happen to be sort of, as indicated, up and to the right, then you can perform a measurement on that state of spin. And if your measurement is to say, is your spin in that particular direction? It will say, yep, with certainty, yes, that is my direction. But if you try some other direction, then it's, or if you could say, you see, you can't ask the state of spin, hello state, which way are you spinning? It just looks blankly at you and says, I don't answer questions like that. Choose the direction and then I'll tell you an answer. Now, if you happen to choose the right direction, then it will say, yes, with certainty, you got it right. If you choose some other direction, it will just give you probabilistic answers, depending upon how far off you are. If you're nearly right, it'll say, usually it'll give you the right, it'll say yes, occasionally say no. If you got it at right angles to that direction, it'll say 50% right, 50% no. If you've got the opposite direction, it will say no every single time. So this is the way you have to understand quantum reality. You can't ask the state what its reality is. You can confirm what it is. So it's a question of confirming rather than ascertaining. Classical reality is something you can ascertain. Quantum reality is something which you could confirm. If you get it right, if you've got it wrong, it will just give you probabilistic answers. And it's important to make this distinction. Otherwise, it doesn't seem to make sense of the way the world works. So classical reality, I have now a picture of the sort of thing I mean. At the bottom, it is a space-time picture, roughly speaking. So time is sort of going up the picture, sort of sloping off to the right, if you like, going up the picture. At the bottom, we have a laser which is aiming a high-energy photon at a beam splitter, or a half-silvered mirror, if you like, and it splits the photon into going horizontally and going down. And so that means that the horizontal state, it hits this little lump of material, a speck of dust or something, a little tiny grain there. It hits it, and this thing then starts to move by the impact of a photon in it. If it didn't hit it, it's left in the same place. Now you follow the evolution of this thing as you go up. It starts to be in a superposition of two locations. It keeps on as you go up into two locations, and then the collapse happens, one of them disappears, and it becomes the other. Now, the quantum reality sort of tries to follow both branches at once in some way. The classical reality follows the left-hand branch because that's what the answer happens to be. But there is something kind of still curiously retroactive about this. It seems to go backwards in time to establish what the reality is, which is a kind of strange idea. But it seems to be what you need in order to make sense of things like this. This is a sort of Einstein-Podolsky-Rosen type of experiment where, again, it's a space-time picture. The picture is going up from bottom to top. Right at the bottom, well, the left-hand one is called Alice and the right one is called Bob. For some reason, they're always called Alice and Bob. A and B, they are. And they are given a spin zero state, which that means when it's split into two halves, Alice takes the one half and Bob takes the other half. So it could be, say, two electrons or something like that. One spins in some way which is opposite to the other one. However, it's not very determined which way it spins. The state, the quantum state, is that it's a superposition of Alice being spin one way and Bob the opposite, and Alice the opposite and Bob the one, or if you like that, but it's a completely symmetrical state. And you can follow the evolution of this as it goes up, and then at a certain point, Alice makes her measurement. She chooses something, if you can see the
at the right top left part of the picture, she tries to measure it sort of angled upwards and to the right a little bit. And the state says, no, that's wrong. And so Alice's state comes to the conclusion it must be the opposite. And then Bob's state instantaneously, well, it's worse than instantaneously, because you have to look at the thing, make it realistic, to make it consistent with special relativity. And the only way you can do that is that Alice's state, the quantum reality of her state, propagates backwards along the past cone. So you can see these sloping lines through this point where Alice makes her measurement and goes back and hits Bob's state. So Bob's state becomes spinning the opposite way to Alice's. And that is the quantum reality of the state. Now, if Bob could ascertain what that state was, you would be in real trouble, because that means you could send signals faster than light, and space and special relativity would be out the window. There would be no way of making sense of special relativity. Special relativity only makes sense because you can't send signals faster than light. So Bob, since it's quantum reality, Bob's state, but at the point QB, I think you can see it, you follow the diagonal line off to the right hand from the measurement that Alice had made, and it retroactively changes Bob's state to be the opposite of Alice's measurement. She said it measures, well, it's the same as Alice's measurement because it's the opposite of what she finds, put it like that. So it's now become the quantum reality of Bob's state. Same way that Bob makes a measurement even later than Alice, and along his past light cone, it has influenced Alice's state. You could say that the quantum reality of her state was already fixed by the time she measured it. Now, it's a pretty crazy picture, but it seems to be completely consistent. This tells you the quantum reality of the whole situation, which completely consistent, looks crazy because it involves these retrocausal effects. So you have to say that these retrocausal effects are really there, but they're only in quantum reality, so you can't really ever sort of make use of it in an experiment. However, it may be, now here, it goes back to things which I have talked about before. In fact, this picture comes from The Emperor's New Mind. It was already there, and I already worried about these things. It's an experiment due to Benjamin Libet, where he had an electrode attached to a patient's finger. The patient was undergoing I believe it might be illegal to do these operations now, so have to be done in a different way. But the patient was having an operation on the brain, which meant that the brain was revealed. And during this operation, the patient had given the experimenter permission to do an experiment at the same time. So the experiment involves stimulating the finger, and then you can see at the top, the stimulation of the finger is that little vertical line. And you can also stimulate a part of the brain which was concerned with sensing what has happened to the finger. Now you can measure the brain stimulation. Sorry, I have to remember what my picture is doing. The finger stimulation is their vertical line, and there is a fast-moving clock in the room, and the patient looks at the clock and tries to say whether the finger stimulation took place at a certain moment, and it is pretty well simultaneous, just very slightly, tiny events, almost simultaneous with the stimulation of the finger. But then that's looking at the fast-moving clock, and all it means is that the sensation of the finger is judged as being simultaneous with the sensation of where the hand of the clock was. But that seems to be almost simultaneous. Now, if you stimulate the brain, that's the second line there. That's the wiggly line. Stimulation of the brain, there is nothing felt by the patient until about, I think it's a half a second, a quarter of a second later. I can't remember. No, nothing is felt. Sorry, nothing is felt until half a second later. That's the third line down. So the stimulation of the brain is felt, but about half a second later. Then the next line down, that's the fourth line down. If you stimulate the finger first, then this is the curious one, because the brain stimulation, although it was later, somehow seems to cancel out the finger stimulation, even though the stimulation seems to be simultaneously with what the clock said. So how is it that the later stimulation of the brain somehow could wipe out something which seemed to have occurred earlier? Well, that's a puzzling thing. And I remember worrying about this, that maybe one's conscious experiences could be delayed something like by something like half a second or something like that. But then you have to worry about things like if somebody is playing ping pong, or, well, I used to play ping pong when I was at university. And it seemed to me if I was going to decide whether to hit the ball one way or the other, that depended on looking at what I thought my opponent was doing, and whether my opponent would be more expecting the thing to go one way or the other, then I'd flick it the other way. Now, the current view is that's all done unconsciously, and I said, no, I was thinking which way to, I did that conscious thinking about. But somehow it seems to be that this conscious impressions are backwards referred. Now, the question is, can you make sense of all this in such a way that if the collapse of the wave function is what's involved in the choice, I mean, that's the view which we have in ORCOR, the ORCOR proposal, is that it is the collapse of the wave function which is involves in making a conscious decision, then that would have to be something where you study how the collapse of the wave function works, and it has this intrinsic retroactive aspect to it. You have to be careful that it doesn't cause causal loops which are inconsistent, but nevertheless, if it's not causing some kind of inconsistency like that, you might explain in some way how effects can be retrocausal in this strange kind of way. I think that Stuart has some certain ideas about this, which struck me as quite plausible. And the idea is if you have an athlete, not just me playing ping pong, I'm not an athlete, but if you imagine a real professional, then deciding whether, say, a tennis player, or deciding whether to hit the ball down the line or cross court, then that decision, all the muscle movements and exactly what to do must clearly be unconscious, because in order to hit the ball to the left, the player doesn't decide which muscle to move in which exact way. All that thing is done unconsciously, sure. But the actual decision as to whether to make one choice or another, that could be a conscious decision, which is somehow retrocausally, in this way, goes back effectively in time. As long as it doesn't cause a causal problem, that's okay. Now, the argument I was making before about free will, see, free will, I often wondered about, does it mean anything to say you have free will or something? Now, free will, I remember I used to play my younger brother at this paper, stone, and scissors kind of thing. And I got very alarmed because he used to be able to beat me almost consistently. And I thought, well, look, I'm trying to be as random as I can. How can he beat me consistently? So what I did is I went into my father's study and I took out a volume of logarithms, and I opened it in the middle of the page, and then I made a sort of random from these logarithms, taking them as basically random numbers. I could code, which I did, scissors, stone, or paper, and I just made a long strip of paper, and I followed this, which seemed to be pretty well random. And then I broke even. My brother couldn't beat me if I was doing something which was effectively random. Of course, it's not random, it's just logarithm thing, tables, but it was effectively random. But the thing was that he could recognize patterns in what I was doing, and I was trying to be as random as I could. So the argument I'm trying to make here is that it's not consciousness if it's doing something which is based on the collapse of the wave function. It has to be something which is not random. It's something beyond random in some sense. It's something which may involve quantum realities,
which are not random, and that's way beyond anything we can think of now. And certainly, when you think of making a conscious decision, the whole point of it is that you go back to decide whether it's a good idea or not to make that decision, unless you're trying to be random, of course. But if it's something which might be beneficial to do A rather than B, then you have reason to believe this. And it comes from your conscious understanding of whether it's a good thing to do or not. So that's the kind of argument I'm trying to say. Conscious understanding is something which involves the collapse of the wave function in some theory which we don't have yet. I regard this as one of the big challenges of physics, to find a theory, and it's clearly going to be a very strange kind of theory, which involves this kind of retrocausality. But nevertheless, theory which somehow involves gravity at the same sense time as quantum mechanics. It's not quantum gravity because quantum gravity means applying quantum mechanics to gravity. It's gravitizing quantum mechanics. And so far, I think nobody has got very far with that at all. I'll have to leave you with that wondering. Thank you very much.